So, I'm very, very pleased to see such a well-crowded room. Welcome everyone here in the Schönfeld Hörsaal as well as online. The colleagues gave me the sign, we are ready to roll, and I'm very, very happy to greet our guest of honor, Roberto Calandra. We are very pleased to do this inaugural lecture with you today. And of course, I'm greeting everyone from the TUD community. And I just said to Roberto, he has quite a following. The crowd came out for him, even with the snow out there. And so I think you should really take it as a compliment. And so what are we here for? We are here for, of course, Roberto Calandra, but we're also here for robots, right? So robots, they inspire us, and they have inspired countless science fiction novels and movies, and they engage our fantasies like almost no other object, for whatever reason. At the same time, we have respect for them, right? And sometimes we even fear them, and we are not so sure whether we are always and will always be able to control them. So it's this fascination for robots, or I should say robot-like creatures, such as Golem. They are centuries old, and they are an important piece of human culture, of human history across and around the globe. I'm sure of it. We have always been fascinated with making things move and making them human-like. And so with AI and robotics and its increasing progress, self-governed and moving machines are gaining more and more attention and relevance in science, in industry, and in the end for the productivity of our societies as well. And we know them all in our everyday life. We know them, they help to clean our floors, they help to mow the lawn, but also they help to do very important things in the clinical field. They do operations, they help to do operations. So there's a big area of application in medicine and caretaking. And of course, since a long time in industrial production, they have taken over the very heavy and difficult work, for instance, in putting together the Germans' most beloved gadget, a car. So VW has been using them since decades. And of course, needless to say, TUD and its partners in Dresden Concept Alliance is highly engaged in this field, in this dynamic field of research and technology transfer. And like always, we do it in a very unique manner. Why do I claim this? Because here at TUD, when we research robotics, it includes researching the hardware, it includes researching, of course, the software, and, but no means lastly but not least, often overlooked crucial part, we are also researching the information transmission, because no robot can work without the information. Here, this object needs to move and to work and to act. And so it's highly interdisciplinary, and that is what TUD is known for, very low threshold interdisciplinarity, and disciplines interact on equal footing with each other, ranging from electrical engineering, mechanical engineering, of course, to computer science, but also behavioral science and medicine. And I'm just mentioning the most central ones when it comes to robotics at TUD. The center of gravitation at TUD, when it comes to this very exciting field, of course, is CeTI. CeTI, our Cluster of Excellence, full title, you all know it, Tactile Internet with Human in the Loop. And so researching real-time interactions of humans and robots with a focus on the use cases of medicine, industry, and the Internet of Things. But we also have a future robotics lab, and we will hear about this from the Dean of Computer Science. And we have infused our teaching and the curriculum, of course, in electrical engineering, but also in computer science with robotics, and to bring it to the students as early as possible because it's exciting and we want to make our contributions. Last but not least, we have numerous spin-offs, and to show how strong our research is and our technology transfer is. And of course, our flagship to date is Mandelbots. So if you haven't heard about them, if you don't know about them, go to the website, and they are always looking for eager and interested students to work with them. Now, of course, in Dresden and vicinity, we have associations of other actors in the field. I mentioned Dresden Concept, but also startups and companies have gotten together, and they formed an association called Robot Valley Saxony. And it's in the heart of Europe. And just like we are one of the hotspots of semiconductor production in Europe, we are one of the hotspots of robot research and of robot startup creativity. And it is exactly in this ecosystem that we lured Roberto Calandra to come and join us, and we are very happy about this. And he has been the chair for Explainable Artificial Intelligence since March 2023. And he is one of the principal investigators of CeTI. Needless to say, we will hear more about this. I will not go into detail of his CV because Soo-Chin Lee, the vice PI, the co-chair of CeTI, will speak to this, and the Dean of Computer Science at TUD will speak to the relevance and strategic importance of this professorship for his faculty. So, it is needless to say that Roberto is enriching, and by bringing his portfolio of experience, international experience, to our university, you're significantly enriching our research in robotics, and particular, of course, with regard to machine and deep learning, tactile sensing, and artificial intelligence. And you came from a world-renowned AI research institution as well as companies. We're not mentioning names, but maybe someone will do later. So we are very happy to have you as a person bridging the gap between the company applications, the fundamental research that we conduct so well here at universities, and you're exemplifying this in an ideal way. So we are bidding a very warm welcome to you, Roberto Calandra, but at the same time, before you applaud, we are welcoming your family. And this is, of course, Radica Stojanovic, your wife. She is chasing the two sons, Enrico and Dario. Welcome, you three up there. It's great to have you here. So, this is crucial to bring the community together, because outstanding research, outstanding science needs a context. It needs support, not only from the university and its institutions, but also privately. And so we are very happy that you have such a great family around you, and we do everything to keep you all happy. So what do we need to make robots useful? This is one of the questions that Roberto will ask later in his lecture. And I'm handing over to the Dean and then later to Soo-Chin Lee, Professor Soo-Chin Lee. And before I do that, I'm thanking the organizers, my Chief of Protocol, Christine Milkau, like always, but also from the computer science, Sylvia Kaplusch, not sure whether she is amongst us, who I was told helped prepare. And we have the colleagues from the communication office that help us stream and advertise the event beforehand. And like always, We have a reception, so stay on, don't run away. We have a chance to toast to Roberto and his family later on. And so without much further ado, I'm handing the mic to Ivo Spalzarini, the Dean of Computer Science at TUD. Thank you.
Thank you very much, Ursula. Thank you, everybody, for joining. It's fantastic to see this room so full, to honor Roberto Calandra as our new colleague. And coming back to what the rector has just told us about the mystical and literary importance of robots, I am personally less afraid of human-like robots than of robot-like humans. And so I very much welcome Roberto's research, who is looking into how to make robots more human-like. And as we all know, there are two things, mostly, that distinguish robots from, there are more than two, but two things are very important that distinguish robots from humans. One of them is that humans have a very good sense of touch. And there is something called affective touch. When somebody touches you, you can feel whether that was a supportive touch or whether that was a punishing touch or whether that was an affective touch. And robots cannot do that. Robots maybe have pressure sensors that they can regulate how strongly they touch something, but they cannot really transmit emotions via touch. And I think that's one area that Roberto is hopefully going to talk about, where I know he's one of the world leading experts, and that will make robots more human-like. The other thing that humans can do is, usually at least if they are reasonable humans, they can explain you why they took a certain decision or what made them think in a certain way. And that is the fundamental question of explainable AI. And again, that's something that AI-driven robots, especially when they're based on things like deep learning or reinforcement learning, at the moment are not able to do. They behave in a certain way because that's what their internal machine learning algorithm has learned, but they cannot explain you why they behave in this way or how they have learned behaving in this way, and that's the explainable artificial intelligence part of what Roberto is working in. So I'm very happy as Dean of Computer Science, I have to say current Dean of Computer Science, that we managed to attract Roberto, who is really one of the international outstanding, most outstanding researchers in this field, and we lured him away from the comforts of Silicon Valley. Big thanks for this goes to my predecessor, Uwe Assmann, who was the dean of the faculty at the time and successfully negotiated with Roberto and convinced him to leave San Francisco and come to Dresden. Now, I'm also personally very happy that Roberto is here because we share at least two things in our lives. We both spent some times of our life in the Bay Area. I don't know where you lived. I lived in Foster City and in San Mateo. We know that this is a fantastic place to live, but we also know, at least I know now, and hopefully Roberto also soon, that Dresden is a fantastic place to live. And the other thing we share, of course, in life is that both of us have Italian roots, with the main difference that I'm from the good part of Italy. So Roberto, big welcome in the faculty. Of course, this professorship is of central importance for computer science because it links three of our most important strategic activities, and the rector has already mentioned them. One is robotics, where we have just founded, again with Uwe Assmann and 19 other colleagues from electrical engineering and mechanical engineering, a lab, a future robotics lab, also Roberto is involved in that, on the level of the School of Engineering. So robotics really is probably the most unifying research topic across mechanical, electrical, and computer engineering, and that is one of our strategic foci, and also the industry that is developing, as the rector has pointed out, in and around Dresden in the area of robotics is, of course, fostering that. The second thing that Roberto links is the CeTI Cluster of Excellence, and Shu-Chen is going to talk about that. It's one of the 3 clusters of excellence that we have here at TU Dresden, one of the 2 in which the Faculty of Computer Science is involved in a leading role. and we are very happy that this joint appointment with CETI and computer science could be brought to life in the person of Roberto, who really embodies the unification of all of these topics of robotics, human in the loop, also the branching out to psychology and behavioral science that CETI does, which is really interdisciplinary and unique, and also the branching out towards more medical applications and life science applications, where we as a faculty are very heavily invested with, for example, the Else Kroner-Fresenius Center for Digital Health or the Center for Systems Biology Dresden with the Max Planck Society, where we are, at least in Europe, if not in the world, leading in the area of computational life sciences. And so also that is something that the hiring of Roberto is going to further strengthen. And last but not least, it's AI. In this case, explainable AI, which really was a missing puzzle piece that we didn't have, which I think is a very important puzzle piece to have if we want to make AI technology socially acceptable and interactable with humans. And it fits perfectly and is perfectly complementary to all the AI research and activity that we have in SCATS AI, one of the BMBF federal centers of competence for AI, in CeTI, one of only 3 schools of excellence, graduate schools of excellence for AI in Germany, and all the other AI initiatives and professorships. Our Institute of Artificial Intelligence is really growing like the sweet pudding, and I'm very happy about this, and Roberto is also perfectly connecting into that. So without further ado, I will hand over to my colleague, Xu Chen, and thank you very much, Roberto. Thank you for doing this. This is also great, and a big welcome in the Faculty of Computer Science.
So, I'm the third in the line. My job is to give a laudatio to our center of focus today. There he is. Dear Roberto, and dear rector, and dear colleagues, and dear students. Now, it is really my great pleasure, you can see my movement and the way I talk, for me to welcome you, Roberto Calandra, as a professor at our university and a principal investigator at the Excellence Cluster CeTI. I wouldn't take too much time to make commercials for CeTI. You can see us at our webpage, and we are working very hard now trying to get the next funding phase, not just for us, but for the fund and for our very synergistic university. Actually, the very mere fact that I, as a lifespan developmental psychologist, have the honor to give the laudatio to welcome Roberto as the 4W3 professor for this newly established chair of Explainable Artificial Intelligence that is hosted in the Faculty of Computer Science. This clearly shows that TU Dresden is a very synergistic university. And besides striving for excellence and synergy, our university also highly values internationalization. Without this, you wouldn't see already, 3 of us here, and we are very happily feeling home here. Now, when looking at the academic and career pathways of Roberto, one can really say that he truly is a global player with immense energy, plasticity, and efficiency in learning and adapting to many new situations, including climate change. I mean, literally, climate change. And he originally comes from the sunny Sicily, the warm side of Italy, and obtained his bachelor degree in computer science engineering from the University of Palermo in 2011. Students, keep the numbers in your mind. Then he moved up north, I mean, way north, up north to a much colder climate, and pursued a master's degree in machine engineering and data mining from Aalto University in Finland. He then moved to Germany and then obtained his PhD in 2016 from TU Darmstadt. Now, notice this was only 5 years after he completed his bachelor's degree. After that, he took up a postdoc position at UC Berkeley in the United States, and in 2018, he moved to the exuberant Silicon Valley nearby, where he joined Meta AI Research, formerly Facebook, and later on, he also founded his own robotic lab in Menlo Park, until we very luckily could attract him to our university, to the the Faculty of Computer Science, to the excellent cluster CeTI, and the Saxony Robots Valley last year. No? Now, if I now return to the theme of our synergistic university and synergies in sciences, then among many other very innovative aspects of Roberto's research, which we will hear soon from the maestro himself, what fascinates me that most as a lifespan developmental psychologist is the way he approaches the sciences of AI and robotics. In his research program, he furnishes robots, big or small, thin or humanoid, with mechanisms and hardware for sensing the light, the sound, the touch, and smell. And very much like our human brains, perceive a great varieties of changing and sometimes noisy physical and chemical signals from our environment through our fantastically fantastically evolved sensory organs. And moreover, Roberto develops very sophisticated computational models and algorithms to allow the robots to learn through actions based on principles of reinforcement learning and also principles of Bayesian statistical methods for abstracting information, patterns, and even meaning from uncertainty, from the uncertain environment. And in this way, in his research, Roberto makes it possible for robots and AI algorithms to learn through experiences with errors and positive feedbacks, rewards, in a similar way that how you and I learn, develop, and grow. And it's wonderful to see your two boys and your lovely wife behind there. Now, it is really wonderful to have you, Roberto, joining us all at TU Dresden and CeTI. I look very much forward to many collaborations and opportunities to discover and understand the similarities and differences between artificial and human intelligence through interdisciplinary breakthroughs to make AI more explainable in your lab. And we, on the other hand, work hard to gain deeper understandings about human perception, cognition, emotion, and their development. May there be many transdisciplinary outputs and products that could provide humans with cohabitable AI systems and robots to further augment our human capabilities for reaching horizons that human societies have not yet seen, but I have to say also very importantly at the same time, hopefully we will also find ways to avoid potential negative effects of AI on us. Maestro Roberto, please come and tell us about your learning machines, please.
All right. Thank you very much to the rector the Dean of Computer Science and the speaker of CeTI again for introducing me, the kind words, and for welcoming me here again in Dresden. And thank you all for taking the time so late at evening to be here today. What I would like to convey the message today, and what I'll be talking, is the topic of intelligent robots. How do we get there? What are the steps that we need? And very briefly, some of the work that we are doing and have been doing over the years toward this goal. And I'll try to get rid of. Oh, I don't know how to do this. Fine. So, why robots? Robots have the potential to be a revolutionary force for good in our society. If we were to have robots that are truly capable of doing the things that we see in science fiction movies, we would be able to further automatize industries. We would be able to replace kid workers from the coal mines of Thailand. We would be able to improve the performance of our industries in the westernized world. And we would be able to fundamentally remove labor that is, potentially boring or dangerous for people into everyday life. At the same time, robots might be useful for helping in case of disasters, in case of hurricane, earthquakes, to provide fast and immediate help in finding survivors that are in places that are hard to reach with human rescuers. Exploration. We already have seen how exploration of difficult environments and dangerous environments, like interplanetary exploration and exploration of the depths of our sea, it's already carried out through robots, not through humans. And this is not only for safety, but also for convenience reason, because it's easier to send a robot, let's say, 10,000 kilometers away from Earth, rather than send a person that needs to breathe and need to get food and so on. And finally, medicine and elder care. As the population of westernized societies like ours grow older, we will need more and more people that can help us as we grow older as well. And hopefully having assistants that are robotics, that are able to assist us in a personalized manner and into our home will be a great way of reducing the burden onto our healthcare systems, and also maybe to make our life a little bit better at the personal level. However, if we look at what is the reality of robotics nowadays, it's pretty far from the science fiction movies that we see. These are videos taken from the DARPA Challenge in 2015. These were the best team in the world, spending 4 years of their time, hundreds of millions of dollars, and we team up to 100 people in order to program robots to be able to navigate a relatively simple path that any human can walk through, opening doors, doing simple tasks, and the outcome, as you can see here, are failures that nobody as a human would ever do. My kids, which are up there, they would never fail to open a door and fall backwards. And I'm very happy to report to the rector that if you close your door, you are safe from all, robot overlords, at least at the moment. So, why are the robots failing like this? What is the problem with, with the way that we currently design and program robots? Of course, there are many components that are missing. And fundamentally, the questions that I'm interested in answering, throughout my research and in our lab, is what are these components? What do we need before we are able to deploy robots in the real world in a way that is meaningful, in a way that is safe, and where we can truly interact with people and help them into their home in unstructured environment outside of lab and in our everyday life? And coming from the world of artificial intelligence, at least part of the answer to me is that we need to replace the traditional algorithms or complement the traditional algorithms that we use for controlling robots with artificial intelligence in order to be able to give them the capability of better adapting to the changing condition of the world, to the uncertainty of the world, to the messiness of the world. And fundamentally, this is one of the two missions that I'm interested in challenging and developing into our lab, laser lab, of fundamentally making robots more useful in the real world through the use of artificial intelligence as a primary tool. On the other side, there is also a very fine and subtle philosophical point, which is that as we develop better algorithms to make our robots more useful, we are also investigating the nature of intelligence itself, especially in our current artificial intelligence community. Many people believe that it's possible to have general purpose intelligence just by training from images or data sets that we can find online. However, if we look at the world around us, the only example of intelligence that we are aware of is embodied intelligence. It's humans, it's animals that have a body, and the body, it's very likely to be heavily shaping the way that we learn, the way that we sense the world, the way that even the algorithms that we use are constrained from the body and shape of our physical manifestation and the environment in which we interact. And of course, there are many, many challenges in order to be able to have robots that are useful in the real world. And these challenges go all the way from how do we build hardware that is appropriate for this task, all the way down to how do we build software that is capable of understanding and controlling these robots. And among these challenges, there are three in particular that we are currently focusing on, which are multimodal sensing, adaptive hardware configuration, and quick adaptation to new tasks. And throughout the talks of today, I will be talking about some of the solutions to these three problems. And I will now be starting in particular from how do we adapt robots, or how do we allow robots to learn and adapt to new tasks quickly through the use of reinforcement learning and other decision-making algorithms that we develop. And when it comes to decision-making under uncertainty, we have a toolbox of different type of algorithms or families of algorithms that we've been using over the years. But the one that we are most, I would say, fond of is reinforcement learning. It's the idea that we would like robots, in the same way as humans learn, to be able to learn through trial and error. We would like a robot to be able to learn how to grasp an object by trying and failing until they finally understand what are the important aspects of this, and they can finally achieve their task and solve their task. And this is an iterative process that we also see in humans as well as animals everywhere, which has different challenges. One of the challenges, which is certainly very important, is the data efficiency. As humans, you are able to learn a new game that you have never played before in 10 minutes. At the moment, artificial intelligence and reinforcement learning algorithms, even the most successful one, like AlphaGo, that beat human-level champions in Go and chess and whatnot, require extreme large amount of data, equivalent to hundreds of years of experience for a person. So how can we deploy a system in a robot without having to wait hundreds of years before the robot learns how to solve the problem, how to open a door? This is, of course, very important. Uncertainty, how do we deal with the messiness of the world? Computational efficiency, how do we make sure that our robot is capable of making decisions within 2 milliseconds before falling down on the floor? How do we make sure that this whole control is robust enough that we can deploy it in the real world, again, in a safe manner? And I will now show you a few videos, which I hope will be engaging and fun, of different applications of these algorithms over the years in different fields, but mostly robotics. And for sake of time, I will not go at all into the details of the mathematics behind it or the specifics of the algorithms, but I will be mentioning the papers, and I'm happy to talk about the specific algorithms offline after the talk, or if you're interested, you can just read them from our work. And I will be starting from one of the first works that I did many years ago during my PhD, where we had a small bipedal robot, a quasi-passive dynamic walker with springs, extremely difficult to control. And the PhD before me spent 2 years in order to design a controller which was capable of walking. And my job was to instead create an algorithms that we deployed in the real world and was capable of learning how to walk in a day. And the robot was, through trial and error, attempting to walk, and initially would fail, and over time it would get better and better until by the end of the day was able to walk with the same performance of what the PhD student spent 2 years coding. And this was without any knowledge on my side about this particular robot or this particular structure of the biomechanical controller used to control the robot. It was everything entirely learned from data. This is great. The same type of algorithms, we also use them later to learn how to walk with simulated micro-robots that were capable of learning not only to walk as fast as possible, but also to make trade-offs between different objectives, such as the speed of the walking and how much energy they were using, so that in different opportunities you can decide what's the trade-off that you want to have. If a bear is running after you, well, you probably don't care so much about energy. You just want to go fast. If you're taking a stroll in the park, on the other side, you don't care about speed. You're just enjoying your walk, and you can be more energy efficient and enjoy it more. And we were also able to discover new gates that don't exist in nature, which was kind of a side project. We also deployed this for the learning of and optimization of hardware configurations of robots, so that we were able to discover different morphologies and their respective controller that were able to perform better in different environments. For example, uphill or downhill. And then we went to biologists at Arizona State, and when he looked at these morphologies that our algorithms automatically discovered, he was like, oh yeah, these are the two morphologies that we find in insects. What were you expecting? This is the posture that insects take if you are on granular media, and this is the posture that insects takes on harder surfaces. And we were like, well, that's great. We didn't code this. It just naturally arises from the data and the optimization. We also developed algorithms that were able to leverage on a lower scale the dynamics and the physics of the world. In this particular work, we learned dynamics model that are able to predict the effects of our actions. So, for example, if in the model we say, okay, this is the position of my arm, and I'm now going to contract my muscles, where is the arm going to move? And in the moment when we learn these causal models of the world, we can then use them for predicting the effects of our actions over a longer horizon, and eventually for planning what is the best sequence of actions that we want to apply or we want to perform in order to achieve a desired goal. And this at the time was a very successful idea that we were one of the first to demonstrate in the context of deep learning. And the results were algorithms that were capable of learning how, for example, to run with simulated robots in extremely short amount of time. So compared to model-free algorithms, this SAC, that was the state of the art at the time, which required millions of interactions, we were able to learn how to run within 50 trials. That's order of magnitude faster. And this means that we are potentially capable now of deploying these algorithms on real robots, because 50 trials is something that we can actually do on a physical hardware. We also deployed this, or we also try to give the capability of robots to adapt better to changing environment. Here's an example of a quadcopter which has learned how to fly, but is also capable on the fly to capture new payloads and dynamically adapt the trajectories and the flying capability to compensate for payloads that are heavier or lighter. And this was very cool. Overall, we applied the algorithms that we developed to a fairly long number of problems. Some of them are robotics, but more generally, the algorithms that we develop are applicable to any decision-making problem that you can think of or that you can formulate in a mathematical way. And beyond learning to walk and flying and grasping with robots, we are able to control ferrofluid droplets, for example, to deliver drugs in a very precise way inside simulated human bodies through the use of ferrofluid droplets and magnetic fields to control them. We were able to optimize the design of micro-robots. We were capable of optimizing bioreactors to be more efficient, to be able to regenerate bones faster than what people would normally be able to design. We were also, as a part of a really cool project that we did a couple of years ago, we were able to speed up MRI machines, which is a major problem in medical applications, because taking an MRI at the moment takes 1 hour or so. And so the main bandwidth of whether you can take an MRI when you need it is there space and time in the machine? And we were able to show that we can speed up by about 4 times the time necessary to take a scan by adaptively optimizing the frequencies that the MRI machine is sampling on the patient. And finally, we use some of these algorithms in real-world for the real-world optimization of processes at Facebook on planetary scale. Now, as I've mentioned before, I've not gone into details of what exact algorithms we are using, and we've developed a very large variety of them. But if you're interested, I'm super happy to talk about this offline if you have questions. However, I will now move on to another topic, which I think is very interesting, and in which we've been focusing quite a lot of effort over the last few years, which is touch sensing. And the idea here is that touch sensing is one of the most important sensing modalities that we have as a human. You can be born blind, you can be born deaf, you cannot be born without the sense of touch. And we use touch extensively into our everyday life, even when we barely realize it. Every time that you are lifting an object, every time that you are leaning on a table, every time that you are taking steps and you are keeping your balance, what your brain is doing is that it's sensing forces between you, your body, and the environment. And in order to do this, we heavily rely on our use of touch. We heavily rely on the mechanoreceptors that we have on our skin to measure forces, geometry, vibrations, and all the other informations that we get. And we have sort of confirmations from experiment, for example, from Ronald Johansson, of the importance of touch. What Ronald Johansson did a few decades ago was that he asked people to perform very simple tasks, like lighting a match, and then he would anesthetize their sense of touch while keeping their motor control capabilities. And suddenly, the same touch that you've done thousands of times throughout your life become extremely hard. It takes all your effort, it takes all your really mental activity, and it takes much longer than what you would do naturally if you were be able to sense touch with your fingers. And this is just a demonstration in the case of humans, but we also have demonstrations and proof by now that in the context of robots, as you can imagine, this is extremely useful. And the sense of touch is something that people have been investigating for many years in the scientific community. There are decades and decades of literature about touch, but the main problem that we have had until now is the fact that fundamentally touch is an interdisciplinary scientific endeavor, which really requires people to come at this from many different points of view, from people that build hardware to neuroscientists and psychologists that can help guide some of, how do we make sense of touch and whatnot. And so far in the community, there has been a huge problem of people working at different levels of this interdisciplinarity not be able to put together and work and exchange results and exchange and leverage others people's work. And so something that we've been trying to do very hard over the last year is basically to ask ourselves the questions of how can we lower the entrance bar to the field of touch, how can we improve reproducibility and overall accelerate research by reusing existing components that anybody in the world will can contribute to and somebody else will be able to reuse and build upon. And as you can imagine, the answer to this is in some ways very trivial, which is standardization. If we are able to standardize the field, if we are able to build tools that people are able to reuse, then everything is solved. But in practice, this turned out to be a very difficult endeavor. And over the last years, we've been spending a pretty substantial amount of time and effort and resources toward the creation of an ecosystem of tools that people can use exactly to standardize the research and leverage other people's progress. And I will now try to give you a little bit of a slice of what is our work in this field. But at the same time, I want you to try to understand why I personally feel that this is so important. Because this is not only about giving touch to robots, but this is really about digitizing touch in a way that has never done before. And the historical parallel that I would like to present to you is when it comes to transmission of audio. In the beginning, at the end of the 1900s, of the 19th century, for the first time, the availability of cheap, reliable hardware allowed humanity and people to be able to take a telephone and record audio and transfer it over long distances and then play it back on the other side. And this was not only extremely relevant for our everyday life, our society, industrial applications, but also from a scientific standpoint, this really bootstrapped the creation of fields of computational science dedicated to making sense of audio, understanding how we can transfer audio, understanding how do we do digital signal processing, for example, and more recently, through the use of AI, how do we process this type of audio through the use of artificial intelligence that can now synthesize voices or understand when you talk with Siri what you are trying to convey. And a similar process has happened in the 90s through the introduction for the first time of cheap, mass-produced vision sensors, where we can now take a camera, we can take pictures, we can transfer them, and we can replay them back on the other side. And in a similar fashion as to the audio, this allowed for the first time applications that, business applications that were not conceivable before the use of, such the availability of such mass sensors, but also bootstrapped the creation of computational fields dedicated to making sense of vision that are extremely successful. Computer vision, for example, Bjorn here is our representative. It's an extremely successful field that is now capable of really investigating what are the important aspects of computationally processing vision. And this has huge implication also in our everyday life. into each one of our cell phones, we now have, audios that we can record. We have cameras that we can take videos of. And what I'm going to propose, and what I strongly believe is, that touch is going to be the next breakthrough in digitalizations. We're now at the stage where we are able to mass produce cheap, reliable tactile sensors, and this will allow us in the coming years to be able to sense with touch, to transfer touch over distances, and eventually, when we have appropriate haptic devices, also to play it back on the other side of the world. And this will allow us to communicate better. It will create opportunities for businesses and applications that we can barely even conceive now. And it will also lead to the creation of a computational science field of science dedicated to understanding touch and making sense of touch and processing touch through the use of artificial intelligence. And the grand vision and sort of the way that we have been structuring our research toward this goal is to divide touch sensing into different pillars, which are the components that we think are missing and that we need to develop. And some of these pillars are hardware, touch processing, which is use of AI for making sense of touch, benchmark and datasets, which are extremely important for scientific progress, simulation, and of course, applications and community. We are not going to detail at the moment, but we've spent a huge amount of time and effort, also personally, in trying to groom the community into really allow other people to use our results, to share results with each other, and ultimately to become successful as a community and growing. Just last month, we had the first workshop at NeurIPS, which is the leading conference in machine learning, the first workshop on touch processing, which was a milestone of really the community of AI understanding, okay, we can now start thinking about processing touch. This has never been done before. And so in sense of hardware, let me start from here, and I'll share a few of the work that we've been doing. Now, most of the work that we have been doing in hardware of touch relies on the principle of so-called vision-based tactile sensor. The idea is very simple, and is that against other technology that exists, what we are going to do is that we are going to take a camera, we are going to take structured light, and then we are going to have a piece of silicon on top of it. And whenever we touch this piece of silicon, the light will be reflected in a different way to the camera, and this will create shadows that we can then record and measure. And this is a principle that has been proposed over the years independently from many different people and labs, starting already from the 60s. But more recently, Ted Edelson from MIT has been rediscovering this idea or repopularizing this idea around 2010. And what we did in 2020 is that we designed and open sourced to the community the first low-cost, high-resolution, mass-manufacturable tactile sensor, vision-based tactile sensor. This is a sensor that is extremely easy to use. It's extremely easy to manufacture. You can 3D print it at home. You can cast a piece of silicon. You can order a little bit of electronic online, and it comes to your house, and you can put it together. And this is by far not the best sensors that we can build, but this is the Model T of tactile sensors. This is a tactile sensor that everybody can use and build and have it in their home. And the type of images or the type of readings that you have is something that looks like this. For example, here is a piece of Velcro, and you can see how in the tactile sensor you are able to detect the geometry of each one of the individual teeth of the Velcro, down to a resolution of about 20 to 50 micron, which is in the same order of magnitude of what human skin can measure in terms of geometry. And just to give a comparison compared to leading tactile sensors that were commercially available at the time, the biotech when we published this work was the sensor that everybody would buy if you wanted to do tactile sensing. And the biotech, both of the biotech and the digit are small enough that you can mount them on multi-finger hand for robotics, but the biotech only provides you 29 taxels, while the digit provides you over 300,000. This is 3 orders of magnitude more. And if you want to buy a biotech, this is $15,000. While if you are building your own digit at home, this is going to cost you about 15. This is not an incremental change. This is a significant step change, both in terms of quality of the images that and readings that you can have, and in terms of cost. And of course, Digit was open source, so anybody, including you, can go home, download all the schematics, and build one at home or build upon it. And moreover, in 2021, we further enable and try to make it even easier for people. So we partner with a startup in Boston, and we give them the right to build this tactile sensor, which means that you can now go home and you can order one from their website, and after a few days it will arrive directly at your step in front of your door without having to know anything about silicon, casting, or 3D printing, if this is not what you are interested. And by now, Digit is the most widespread tactile sensor in the robotic community. And recently also, Mitsubishi made it officially part of its robotic ecosystem. So we are hoping to have more and more real industries evaluating and applying tactile sensors into real-world applications. And as I mentioned, this is by far not the best tactile sensors that we can build. And over the years, we also build other tactile sensors with different properties. And I want to keep you in mind, again, this was a sensor meant to democratize touch. Instead, another interesting sensors that we developed was OmniTac, which was a omnidirectional sensor with of 3 centimeters in diameter, which was using 5 cameras to be able to sense omnidirectionally in the same way that a human thumb can. And recently, we extended our Digit family to have also an omnidirectional sensor with a diameter of 25 millimeters, which is functionally equivalent and better in many cases than a human thumb in terms of perception of the world. And we are now in the process of publishing also a new sensor, the 3rd generation of Digit, which is a sensor omnidirectional, but only 15 millimeters in diameter. And in fact, this is so small that we can now mount it on prosthesis. And we currently have a trial in collaboration with Stanford to use it for medical applications to be able to detect cancer and the anomalies in prostates, because this is small enough that you can actually insert it through Da Vinci and other robotics applications inside the human body. On the other side, we've also focused on trying to make tactile sensors more similar to the way that humans are able to sense the world through the use of neuromorphic computing that are capable of sensing up to 1 kilohertz higher and higher frequency, while at the same time reducing the bandwidth necessary to transfer and process all of this data. In parallel to the hardware, we've also been developing simulators. Simulators are very important in science because allow you to test hypotheses without needing access to physical world. And one of our contribution was the simulator Tacto, which was designed to be extremely fast. It can simulate vision-based tactile sensors up to hundreds of hertz. And it can, from a perceptual point of view, it can fairly accurately simulate what a real sensor would be able to outputting if you were to touch and interact with an object. Now, in the moment when we have hardware that sense, and we have simulator that we can use to simulate this hardware, what's really important is the processing. How do we make sense of these raw images, and how do we extract the information that we need in order to be able to control or make decisions upstream? And the problem here is that fundamentally there is extremely limited literature on how do we make sense of touch as a sensing modality, partially because nobody had such an extensive access to hardware before. And so one of our primary goals at the moment is to really bootstrap and create this new science of touch processing dedicated to trying to make sense of touch through the use of artificial intelligence. And this, of course, entails a lot of new questions that have never been asked before, including what are good features for touch? What are the right computational models that we need to use in order to leverage the intrinsic structure and biases that touch has as a sensing modality? What are the equivalent of convolutional neural network for touch? And as a small contribution in this direction, we open sourced the first machine learning library dedicated to touch processing, with the idea that we want to somehow replicate the success and the progress that having a software like OpenCV for computer vision can provide to the community to really drive the progress, provide benchmark, provide baselines that people can use. And of course, we also use, we did a lot of work on our own about representations, including asking questions, can we transfer representation across different sensors or across different tasks? Now, after hardware, simulators, and processing, of course, application is something that I'm very, very interested in, and it's very dear to the work that we are doing on our everyday life. And as you can imagine, there are many applications, most of them still largely unexplored. But just to name a few applications that I'm very interested, certainly it's medical applications. If we are able to provide the sense of touch to people that, for example, lost their limbs, I think that this would be certainly a use I would be very proud in my life. Similarly, medical robotics. If we can really, assist doctors through the use of robots to be able to sense better surfaces and do physical examinations of cancer, breast cancer, abdomen, prostates, this would certainly be of great value. Other potential applications are around the metaverse. How can we digitize objects into the metaverse in such a way that they feel more real, and in such a way that we can potentially also play them back onto haptic devices if you want to interact with the simulated world. E-commerce. I believe that it's not very far away the day where you are able to buy an object on Amazon or any other website, not only by looking at it, but also by saying, hey, whatever, Amazon, buy me a sweater that feels like this. Something that feels soft or cozy or with this thread or with this material of my favorite sweater. And of course, this would have very serious implications from a commercial standpoint. And finally, robotics, which is our core interest. How can we have robots doing more and more through the use of touch? And over the years, we've been working on many, many applications, from learning to grasp to generative models that are cross-modality and reconstruction from vision and touch, learning to play piano better through the use of touch. But in particular, some of the work that we are most proud of consists of systems capable of learning how to grasp objects in the wild, or in objects from the wild. So in this work, we basically collected a data set of over 60 different objects, mostly objects that we hoarded and borrowed from colleagues around the lab. Some of them a random object that we went to a 7-Eleven and we just bought anything that would be less than $10 and would fit inside the finger of our robot. And then we let the robot spend 2 weeks training itself by trying to grasp objects in our environment completely on their own, by just once in a while changing object in front of them. And the result is a system that is capable of successfully grasping object that has never seen before with an accuracy of up to 83%, which is a significant improvement compared to models that only use vision, which is how current industrial robotics is tackling the problem. And some of these objects are deformable objects. Some of these objects have a wide variety of shapes and weight and frictions and materials and whatnot. We also worked on manipulating glass marbles, which is a surprisingly hard task if you are a robot, because if you apply too much force, you are going to shoot the marble from your fingers out. If you apply too little force, you are going to drop the marble. So being able to really manipulate small objects within your fingers to the place that you desire while keeping the right amount of force is very hard. And this is something that we did quite successfully. Very recently, we also developed a system capable of rotating objects that has never seen before. This is using tactile sensors and vision, and is capable of generalizing to objects of any shape. And we had a demonstration of this system at NeurIPS, this machine learning conference, where it won also the best demo award of the workshop on robot learning. And finally, super recent work done in collaboration with collaborators at Meta and at CMU relies on the capabilities, leverage the capabilities of rotating object to also be able to create at the same time 3D models, high-resolution 3D models of this object, and to be able to identify where in this object we are currently touching with our fingers, which is a precursor which we think is going to be very important to be able to do even more complex types of manipulation and even more complex type of grasping. And finally, touch could be used for teleoperations, which is a topic that is, of course, very dear also to CeTI, where we can use haptic devices, we can use haptic gloves in order to be able to sense and transfer from robots to human and vice versa. And already several years ago, we had at the time one of the very first demonstrations of such system, which was integrated onto a humanoid robot, the iCub, and we were able to teleoperate this, this very complex system through the use of an Oculus Quest, so that you can actually, it was not even called Quest at the time, but an Oculus Rift, where you can see through the eyes of the robot, a Kinect that can track your skeleton and map the robot position to the same joint configuration, and a haptic hand that can basically control the fingers of the robot and provide tactile feedback back to the human, so that you can feel very primitive sensation of what you're touching. And of course, this is a precursor also to be able to collect data from humans in such a way that we can then train robots to repeat the same task and generalize the same task without the need to have an operator there 24/7, so that we can demonstrate task and then just have the robot keep doing it. So to conclude, I would like to invite you all, whenever you have time or whenever you want, to the robot lab that we have in the computer science department in APB. It's finally coming all together thanks to the efforts also of Ken, who is sitting up there. And we now have finally a bimanual manipulation system where we can start to replicate and improve some of these experiments and work, provided with also tactile sensors, of course. And we will very soon deliver, we will finally get the delivery of the first humanoid robots that we will have in the campus in computer science, with the hope of really being able to have these humanoid robots be able to interact in real-world scenarios in the houses of people and to be able to walk around the city so that we can really get informations and experience with deploying such system in the real world. And by the way, these are AI-generated images. They're amazing. I love it. Finally, I would like to thank all of my collaborators throughout the years. I was very lucky in having a lot of really, really amazing collaborators, and all of this work I've presented today would not be possible without them. In particular, I would like to thank Michael Ambeta, who has been my partner in crime at Facebook, and he has been very, very important and a very dear friend. And so to conclude, what I've tried to present you today is the line of research that we are trying to establish at the Laser Lab, really at the intersection between AI and robotics. And the main three axes that we plan to keep developing and pushing over and over are the development of new AI algorithms that can make robots smarter, that can be used for better decision-making in robotics and in other fields. The digitalization of touch as a sensing modality that is important. And finally, enabling real-world capabilities that really can push robots to be more useful into our everyday life. And with this, I would like to thank, again, very, very much CeTI, the Department of Computer Science, and the wider scientific community here at Dresden for welcoming me so warmly. And I really look forward to many, many years of exciting and impactful research with all of my colleagues. Thank you very much for being here today.
Thank you very much, Roberto, for this fascinating talk. And before we open the question round, we have a little gift from CeTI.
Yeah, Roberto, on behalf of CeTI, welcome Dresden to you, to your family. I'm looking forward to see nice results in the next time. It's wonderful to see how well you are integrated in our team, even after a very short time. I'm looking forward to see convincing results. There could be something quite big on the university scale when it comes to the next excellent round. I know that you are integrated in a lot of preparational activities, and it would be simply great if there would be a CeTI Phase 2, obviously. Nevertheless, all the best. It will be a pleasure to work with you towards new, exciting ideas. Welcome.
Thank you very much.
So now we have some time for questions, and I would like to remind everyone again that this event is also being live streamed. So when you want to ask a question, please wait for somebody to bring you a microphone, and then ask your question with the microphone so people online can also hear it. There's the first question up there. Now there's some fitness training for the people with the microphones.
Thank you very much for this nice talk. I want to have your opinion. I was thinking about touch and what I would associate with touch. And one thing you didn't mention was temperature. When you, for instance, think about summer and you have a 30 degrees warm wooden table, it feels way different than a 30 degrees warm metal table. So when I touch it, a robot cannot sense, okay, both of them are 30 degrees, but the touch feels different. So how would you solve this?
This is an excellent question. I would refer you back to our to the image of our Digi360 omnidirectional sensor. This publication is currently under embargo, so I cannot discuss it. But touch is certainly something that we do, and we for in humans, and I believe it's going to be as well important for robots.
Okay, thank you very much. I'm looking forward to it.
Was there a question up there? Yeah, Shuchen, go ahead.
Could I follow up this question, dear Roberto? From the psychological or cognitive neuroscience perspective, and also yet another, okay, well, I'm from Asia, but now I'm feeling a bit outnumbered. I'm actually, together you also know Conibetti.
Yep.
So combining senses. And the question you asked back there is a question, now he is not here, so I try to give his due credit. Oh, you were back there. Oh, good to see you, Armani. So can I tell the question? Yeah. So yet another Italian colleague here. So the question is a bit like you know, touching this 30 degree physically the same. How can machine know that? But the question from Conibetti is that if you analyze, he analyzed the chemical structure of smell molecules, that the smell of Parmesan cheese is actually not that very different from the chemical components of something people warmed up. But we humans, of course, if you like cheese, then you, that's the most delicious food, and then the other not. And so the point is that we were discussing is so how humans can differentiating these two aspects, right? And that type of human representation from memory and from different contexts would somehow need to be added to the layer. I imagine from the human way, we are not just trying to do experiments together, have people, touching only a wood, very smooth wood or very rough wood, and then we pair them with the touch of really so smooth or not so smooth, and we try to confuse them, right? And then we can see this expectation, the human expectation about what they are supposed to get, if it match, maybe then they can interpret better. And so in this context, we are not talking about so much the temperature sense, but I thought from my perspective of a human science researcher that to extract the representation and also how humans' anticipation, expectation can affect our sensing may play a role in this question. Yeah, that's somehow, I don't know what you think about that.
I completely wholeheartedly agree. The question of representation is something that I maybe didn't stress enough in this talk, but it's very crucial to all the work we are doing in touch processing. As you said, human representations are intrinsically multimodal. We are able to look at an object and imagine how it would feel with our touch. We are able to imagine how it would feel from, what sound would make if we were to squeeze it, how it would smell if we were to, smell it. So learning multimodal representation in conjunction with vision and other sensing modality, I think is going to be very, very important. We are already partly doing this, but it needs to be extended also to more sensing modality. And another very interesting aspect that you mentioned is how humans basically have representation that are different depending also on their level of skill sets. If you are a normal person, you can look at different, dog types, and you say, oh yeah, they all look like Chihuahuas, yeah? But maybe if you're an expert in dog, you are really able to say, oh no, wait, this is an Indian Chihuahua, this is a different race of Chihuahua. And it's not because somebody sees more, they all use the same eyes to see. The problem is really that the fact that the expert use a different set of representation to understand the same image. And so being able to learn representations that are generalizable across different sensor, different hardware, across different tasks, and that ultimately are learned from data is really, really important.
Great. Then there's a question from the rector.
Well, I would just like to follow up on what Su Chen said. I was very fascinated with the fact that your little stick robots, they learn from scratch. So there was no prior representation of how to walk upright, how to walk straight, how to not fall over. And if we are coming from a frugality perspective in terms of what does a robot need to do what, I would say we do not use a cannon shooting if we can do it with a little kick. And so it will be really crucial to differentiate at what point do we have to extract the highly complex and multidimensional representations of humans, and when should we actually not do it. And of course, if it will allow robots to speed up the learning tremendously,
Yes.
if you start from a prior master representation, then that would be a convincing argument, of course. But I would be very, let's sort of like step by step. I mean, we have a long way to go, and building it the way you did with these very fundamental feedback loops that psychology has discovered a long time ago and received a Nobel Prize for it, even though psychology cannot get it, so it went to economics. But that's really, I was really fascinated with that, and to see how far it gets. And so it's basically a matter of sampling and what exposure do they get, and so what's the database that they can establish, right?
Yes.
So anyway, fascinating.
Thank you. I think this is also a great question. I think that there are two aspects to this ambiguity here. One is the pure scientific investigation of saying, humans seem to learn from reinforcement learning. Let's try to understand more and develop better algorithms for reinforcement learning. But you are absolutely right that if we look from a practical point of view of deploying robots in industrial application or real-world applications, we should try to make use of all the priors that we have, all the inductive biases that we have, and provide to them. And many of the algorithms that we use and that we invented are capable of making use of inductive priors in different forms and shapes. And of course, this is also a very relevant topic for CeTI, where having very strong inductive priors for humans can be very, very important to bootstrap, again, in many potential ways, through pre-trained models or Bayesian priors, eventual behaviors that might be small variations over whatever the prior is ultimately suggesting. And I'm not a neuroscientist, but as far as I can understand, also humans seems to have very strong priors into our motor control capabilities since we are kids. I've partially seen it in my kids, so yeah, I think it's
Great. Then we have the probably last question by our Vice Rector for Education, Michael Kobel, and all the others. Please join us downstairs afterwards. There is a reception. We can toast with Roberto to this great talk and ask him more questions there and engage in discussions. There's enough catering for everybody, so please don't be shy and join us downstairs afterwards for the reception.
Yeah, thank you very much, Roberto, for this fascinating talk and insights. I wondered, as far as I understood, the mediator of your touch sensors is an optical mediator. So you, and my question would be: are there other ways, other mediators for touch sensors? Is this the only way, or is there an open market which is in competition with one another?
This is an excellent question. The thing is the following. People have been developing different technologies or mediators, as you refer to them, for decades. A lot of them rely on capacitive or resistive technologies, for example, but At the moment, none of these technologies are sufficiently reliable, low cost, and robust and high resolution. So vision-based tactile sensors today is the winning technology. Is the technology that I personally expect, at least for the next 5 years, will be dominating the market and will be dominating research. But I also ultimately don't necessarily believe that this is the ultimate technology. If I think in terms of what we will have in 20 years, I think it's very likely that advances in microconductors and silicon and whatnot will lead to technologies that are maybe hybrid between optics and other things. But right now, we don't know what will come. And vision-based tactile sensor, at least in my opinion, just because of the cost and the ease of manufacture and the reliability, is a clear winner. So we are very interested in investigating also other technologies, but we think that for the moment, the hardware is sufficiently advanced that we can focus on investigating applications and really touch processing capabilities that are already way beyond what's, what our current knowledge is.
Great. Then let's thank Roberto again and see you all downstairs.
Thank you.
Bravo. Very well done.
Thank you.
You do really fantastic stuff. We have to talk.
Yes, I would love to.
Because this learning the model, the predictive model from
Yes,
data
this is
something
what
that we-
I've been wanting to talk. Give me a minute.